Here is a problem. You are sitting on a desert island somewhere in the Indian Ocean. You need to repair your satellite phone so you can call for rescue. To do this, you need to find a resistor with a resistance of 125 ohms. You check your repair kit, but unfortunately, all you have is a box full of 1 kilo ohm resistors. How will you solve this problem? Let's find out. In any circuit that uses multiple resistors, there are two major ways of connecting them. You can connect the resistors one after the other like beads on a necklace, and this is called a series connection. Or you can connect them with their ends all connected to a common node, and this is called a parallel connection. To figure out the effective or equivalent resistance between the 2 points in a circuit, we have to figure out what happens to the voltage and current each case, that is in the series and parallel case. In series circuit, the current flowing through the resistors is all the same. You cannot have 1 ampere of flow through this resistor and 3 amperes of flow through the other one, and all the devices in this loop will have the same current. On the other hand, the potential drop in each of these resistors is simply the current in each of the resistor multiplied by the resistance of each. In other words, in a series circuit, the current in each resistor is identical, but the voltages may or may not be different. That would depend on the values of the individual resistances. However, different potential drops across these resistance may be the sum of potential drop across the resistors in a series circuit. That is equal to the total potential difference being generated by the voltage source in the circuit. We can express this mathematically as V source is equal to V1 plus V2 plus V3 etc. up to Vn. Since V1 is equal to I1R1 and V2 is equal to I2R2 and so on, we can rewrite the previous equation as V source is equal to I1R1 plus I2R2 plus etc. up to INRN, as we discussed a few minutes ago. In a series circuit, all currents are identical. This means that we can replace the current I1, I2, etc. up to IN with a single term, that is I. We can model the equivalent resistance of the arrangement as a resistor R equivalent through which a current I is flowing. The potential drop across Req is same as the total potential drop across the n number of resistors. Putting it all together and cancelling out the like terms, we get the formula for equivalent resistance of a series circuit. In a parallel circuit, the situation is in a sense reversed. While in a series circuit, the current in all the resistances was identical. In a parallel circuit, the voltage across all the resistances is identical. On the other hand, while in a series circuit, the voltage drop across each resistance might not be the same. In a parallel circuit, the current in each resistance might not be the same. We can, however, be certain that the sum of the currents in the 3 resistors combined is equal to the total current being supplied by the current source. Since the source voltage is identical to the voltage drop across each resistor, we can formulate a current equation. We can model the source current as Is is equal to V by R equivalent, and that is equal to V by R1 plus V by R2 etc. up to V by Rn. Since V is equal on both sides, cancellation of like terms gives us the equation 1 by R equivalent equal to 1 by R1 plus 1 by R2 etc. up to 1 by Rn. What about a circuit where there are resistors in series and in parallel? Consider the combination of resistors given in this figure. We evaluate the equivalent resistance offered by the resistors connected parallelly, that is the resistors R2 and R3. We'll get that 1 by R equivalent is equal to 1 by R2 plus 1 by R3. This equivalent is then connected in series with R1, and the effective resistance is calculated as shown here. Coming back to the satellite phone on that desert island, we need to make 250 ohm out of only 1000 ohm resistors. We cannot connect them in series as that would only increase the resistance. But if we were to connect 2 of these resistors in parallel, the resistance gets cut in half. If you were to put 3 identical resistors in parallel, the equivalent resistance gets cut to 1/3. So to get 250 ohm out of 1000 ohm, we connect 4000 ohm resistors in parallel and get off the island. We'll see some other interesting properties of resistance networks in the coming sessions. Let us summarize what we have learned so far.
Manorama Horizon. Learning made simple.